Okay, welcome back everyone. We are discussing the Kerr metric, and now we begin with a fairly long section on the geodesics in the Kerr metric. So if you want to know what's going on in a certain space-time physically, so how you can do measurements in the space-time and how the space-time affects things which are floating around, then the geodesic equation is the most relevant equation to study. The light-like geodesics tell you how the light rays move, so they tell you in which way the object distorts or deflects light coming from light sources. And the time-like geodesics tells you how freely falling particles move in this space-time. So if you are interested in particle motion or light motion near a rotating black hole, then the Kerr geodesic equation is a relevant equation. And that's a very rich equation, actually. One often hears a sentence, one can spend his whole life with a Kerr geodesics, which is not much of an exaggeration. And of course, I can give here only a flavor of this, but I will try to tell at least the most relevant and most instructive things. So what was the Kerr metric? Let me write it down again. Of course, we will need the metric coefficients all the time. This was minus c squared 1 minus 2mr over rho squared, was correct. dt squared plus rho squared over delta dr squared plus rho squared d theta squared. And comes the d phi squared term, sine squared theta r squared plus a squared plus 2mra sine squared theta, no, a squared. I forgot the square already last time. d phi squared. And then the mixed term. That's the most important new feature which we didn't have in the spherically symmetric spacetimes we studied before. We have an off-diagonal element, namely a dt d phi square term, c dt d phi. And we need to know what the rho was. The rho was r squared plus a squared cosine squared theta. And the delta was r squared plus a squared minus 2mr. So that's the Kerr metric. And in this metric we have now to study the geodesics. And of course you know the geodesics are given by the Lagrangian. Again a writing mistake.
Is it rho squared or
the description of the metric?
I'm sorry?
The following Lagrangian.
Yeah.
when you define rho?
Yes, rho squared, sorry. Yes, yes, right. So Lagrangian for geodesics. So this was quite generally. So the Lagrangian is something which depends on the axis and the x dots, right? X now stands for the coordinates t, r, theta, and phi. And these are the corresponding velocity coordinates. And this is always given in any space-time by this expression. And here in this case we have how many terms do we have? Let me write this out. We have a term with dt squared, so this gives the t dot squared. So I have a gtt t dot squared, and the gtt is what you can read from the coefficient here. Then we have a mixed term, 2 gt phi t dot phi dot, that's this term here. Then we have a phi term, and we have the r dot term, r dot square and theta dot square terms, plus g theta 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 dot squared. So it's a diagonal terms, this, and this, and one off diagonal term. So when we solved the geodesic equation, well, how did we do this in the case of a spherically symmetric and static space-time? Well, we first observed that we could reduce to the equatorial plane because of the symmetry. So we could restrict to the plane theta is equal to pi half, then this is gone. In all the other coefficients there's no longer a theta, and the whole thing is reduced to a three-dimensional problem. Here we have only three coordinates, t, r, and phi, and their velocity, their corresponding velocities. And we had in this case, in the case of a spherically symmetric and static spacetime, we had three constants of motion. The Lagrangian itself, the energy, and the angular momentum. So we have a three-dimensional problem, three constants of motion. It's a constant of motion when nicely enough behaved so that we could solve for the derivatives. So we could solve for t dot, phi dot, and r dot. So we could integrate the geodesic equation once. The geodesic equation is a second-order equation. With the help of three constants of motion, we could reduce it to a first-order system. And then everything we have to do is just to calculate the integrals in order to get the solution. So if this is the case, if one can solve with the help of constants of motion for the first derivatives, for the velocities, then one says the system is completely integrable. So in any spherically symmetric and static space-time, the geodesic equation is completely integrable. So everything you're interested in terms of the geodesic can be written as integrals. Yeah, you have only to integrate once. You can write it in terms of an integral. In the case of the Schwarzschild space-time, these were elliptic integrals. And now if we have only a space-time which is axisymmetric and stationary, so it has less symmetry. So the symmetry with respect to t and the symmetry with respect to phi give us one constant of motion each. Then we have the Lagrangian itself, which is a third constant of motion, but now we have a four-dimensional problem because we cannot restrict to the equatorial plane. Yeah? The motion will not be in a plane. If you send in a particle under a certain angle, it will not stay in a plane through the origin. Yeah, the plane will rotate. Yeah, the plane of the orbit will rotate. So we have a four-dimensional problem, but only three obvious constants of motion. So it looks as if the system were not completely integrable. Yeah, we have one constant of motion less than we need. And actually, when the Kerr metric was discovered in '63, and when this coordinate system, which we now use, was discovered by Boyer and Lindquist, I think in '66 or so, people actually thought that the geodesic equation would not be completely integrable. But then the Australian scientist Brenton Carter came along and found the fourth constant of motion. So in the Kerr metric, in spite of relatively few symmetries, in spite of this, equation of motion is completely integrable. And that's what I want to, not only to discuss, but even to prove now. So we will go through the whole machinery. So we begin with the constants of motion which are obvious. And then we have to do this, a little bit less obvious calculation which Brenton Carter did in '68 in order to demonstrate that there's a fourth one which is named after him, which is the famous Carter constant. So that's the program for this lecture. I think I will need the whole lecture for doing this. Okay, so let's begin with the obvious thing. So we have three constants of motion. So the first one is the Lagrangian itself. The Lagrangian is always a constant of motion. And let me write this as minus 1/2 epsilon, where I say epsilon is 0 for light-like geodesics. And it is, what is it, c squared for time-like ones. Right? For time-like ones, we always use proper time-like geodesics. So this is the first constant of motion. So the first constant of motion is the epsilon, which takes only values 0 or c squared. Then we have the second constant of motion. That's what we call the energy E. That's associated with a t coordinate. The metric coefficients are independent of t. Yeah, it's a stationary metric. This means that if you think of the Euler-Lagrange equation, if you have dl by dt is equal to 0, if the metric coefficients are independent of t, this means that the Lagrangian is independent of t. And by the Euler-Lagrange equations, this is dl by t dot dot. The dot means derivative with respect to an affine parameter, which in the case of a time-lag geodesic is chosen to be proper time. And well, what is dl by dt dot? Let me use this form here, where I just wrote the metric coefficients in an unspecified way. So this is gtt t dot plus gt phi dot, right? And the derivative of this along the geodesic is 0, so this is a constant of motion. That's what we call E, or rather minus E. Yeah, the usual convention is to call dl by dt dot minus E. The reason is that we want to have positive energies for particles moving into the future. If t dot should be positive for positive E, then I need a minus sign here because GTT is negative if I'm far away from the center. Yeah? d by dt is a time-like coordinate. So GTT is negative in the region where the observers usually move around. And the other equation is dl by d phi is equal to 0, and that's dl by d phi dot. Well, okay, let me write it. So that's g phi phi dot plus g t dot. And that's, well, in the case of spherical symmetry, I denoted this just L, and I will allow myself also in this case, where I have only axial symmetry, to denote it L, but we have to be a little bit careful now what we mean by L. Phi is a coordinate around the axis, our rotational axis. So this is actually the Z component of the angular momentum. Here some people call it LZ, maybe that would be better, but just to spare myself a little bit of writing, I just call it L. But we should keep in mind that it's the Z component of the L. Yeah, not the modulus of the angular momentum. This is not conserved in this space-time. Yeah, what one calls L squared in quantum mechanics. Yeah, just the modulus of the angular momentum. This is not conserved because I have symmetry only about one axis. Yeah, the other two components will not be conserved. Okay, so these are the two obvious constants of motion. And you see, if I forgot the dot here. Yeah, the dot is 0. The derivative is 0, so the thing itself is a constant of motion. So, yeah, question?
And the left side you also forgot.
Yeah, I also forgot the dot. Thank you. So this is the Euler-Lagrange equation here, right? The phi component, that's the t component. Okay, so you see we can solve these expressions for phi dot and t dot. So this gives us phi dot and t dot, fine, as we know, as we have done it in the spherically symmetric and static case. In the spherically symmetric and static case, we just had to introduce the result into this equation, and this gave us r dot, and then we were done. Yeah? Here it doesn't work this way. We can also introduce the expressions for phi dot and t dot into this equation, but we still have one equation for two derivatives, for r dot and for theta dot. And they are entangled, so there's no obvious way to separate this into two equations. So that's a problem which we encounter here. But let me first solve this for t dot and phi dot. So how do I do this? So let me write the equations again. So I have minus E is GTT t dot plus GT phi dot, and L is G. Let me begin with this term so that I have the t dots term one underneath the other one, and the same for the phi dot terms. And if I want to solve this for t dot and for phi dot, it's a good idea to multiply it with expressions so that either the t dot terms or the phi dot terms cancel. So I would have to multiply this with g phi t and this with minus gtt. Let me see what I get then. Oops. Then I get, so I multiply minus e with g phi t, and I multiply plus L with minus GTT, so this minus L GTT. And on the other side I get these two terms cancel, and this gives GT phi squared minus GTT G phi phi. You see that's the determinant of the phi t block in the metric. That's an expression which we will encounter very frequently, and I will calculate it in a minute, and then phi dot. So, and the other, if I want to solve for t dot, then I have to multiply with expressions that these two terms cancel. So I multiply the first one with minus gt phi and the second one with g. No, what did I do here? No, I want to have these two terms cancel. Nonsense. So I multiply this with g phi phi. That's it. And I multiply this with minus gt phi. Okay, then I get minus e g phi phi minus l gt phi is, this gives gt phi squared, the same term, minus gtt g phi phi t dot. Are the signs right? I'm a little bit confused. Because this is negative, so as t dot is positive, I want to have a positive energy. It looks as if I have a negative energy. Did I make a sign mistake? Minus e g phi phi minus L.
Yeah, the sign is wrong.
The sign is wrong, right?
You
G
change in bracket, right?
here. Right? Is it that? Oh no, it does not.
You get GTT times G phi phi should be positive when you multiply. So in the second one, yeah, this is positive. And G phi t times GT phi.
Okay, the second equation is correct, but what about the first? I'm sure I want to call this minus e. Or do I? Maybe not in the mixed. Maybe not in the mixed term. Maybe it is correct. Maybe it is correct. Yes, yes. So if I just to check the sign, we can consider the case that a is 0. Then we have the Schwarzschild case that this is gone and this is gone, and here I have something which is manifestly negative because g phi phi for Schwarzschild is just r squared, and so this should be positive. No, this should be negative. It was manifestly negative, I said, and that's true because GTT is negative and T dot should be positive.
But in the first, it is wrong now.
It's now wrong. Yes, it was correct before. Yes, thank you. Okay, so that's the expression, and yeah, we can read these coefficients from the matrix. They are written there, but we have to calculate this expression here. That's this determinant. So what do we need to calculate? We calculate GT phi squared minus GTT g phi phi. I read this from the metric. GT phi is half this term, right? Remember, this means a symmetrized tensor product. So it is 1/2 dt tensor d phi plus d phi tensor dt. So I have not a 4 but a 2 here for the GT phi. So it is 2m RA sine squared theta over rho squared, right? That's the first term squared. A C, I forgot the C. There's a C in the bracket. And then I need minus GTT. This is plus, what was it? C squared 1 minus 2mr over rho squared. And G phi phi was sine squared theta r squared plus a squared is 2mr a squared sine squared theta over rho squared, if I'm not mistaken. Okay, this can be simplified a little bit. So let me see if I can manage to do this. How do I do this? Yes, I take 1 over rho 4 out of everything, rho to the 4. And then I have this thing here squared, 4m squared, a squared, a squared. And V also a sine squared theta, also a sine squared theta. Then I have only a sine squared here, c squared, plus, the c squared can also be taken out, sorry. It's also in all terms. And then I have multiplied with rho to the 4, so I multiply each bracket with a rho squared. So I have rho squared minus 2mr, r squared plus a squared times rho squared, plus 2mr a squared sine squared theta. square bracket, curly bracket. Again a mistake? Okay, yes, I expected this. I made many mistakes when doing calculations with curved geodetics. There are many, many opportunities to make little mistakes. Just the fact that 2 missing, a square missing, things like that, and everything is completely spoiled. But I do my best. Okay, let's see. Yes, this term cancels against this term here, yeah? Okay, let me write it out and then cross it out. R squared sine squared theta, and now I multiply this out. So I have the rho squared with a bracket. This gives R squared plus A squared rho to the 4th, plus 2m R A squared sine squared theta rho squared, minus 2m R squared plus A squared rho squared, minus 4m squared R squared A squared sine squared theta. And you see these 2 terms drop out. And here I can take a rho squared out of the bracket. Then I have only c squared over rho squared. And what do I have in the remaining bracket? I have, let me see, R squared plus A squared. I think I write rho squared out. R squared plus A squared minus A squared sine squared theta. This is rho squared, right? R squared plus A squared cosine squared theta. And the rest I think I copy. Minus 2mr A squared sine squared theta. Oh my goodness, now I have to squeeze this here. Minus 2m. Is this an R? Yes. R squared plus A squared. And the rho squared I've taken out. So this gives what? Let me see. Yes, let me continue here. In the end, it should become surprisingly simple. Let's see if it works out. C squared over rho squared, sine squared theta, and I have what? I have an R squared plus A squared here and here, so I can combine these 2 terms. Then I have an R squared plus A squared times what? R squared plus A squared. And then from the last term minus 2mr. And from the first term plus minus A squared sine squared theta. And the last term is 2mr A squared sine squared theta. Oops. And this here is, if you remember, just delta. It's still written here. And the rest, yes, I think it works. I think it works. So this is R squared plus A squared times delta. What about the sign? Yes, I think it's fine. I write minus A squared sine squared theta. Then I have R squared plus A squared. And because I have a minus sign in front of the bracket, I have minus 2mr. And that's again delta. So that's fine. So this is delta. This is c squared, rho squared, sine squared theta. Now I can take a delta out, and I have inside the bracket R squared plus A squared minus A squared sine squared theta. But this is rho squared. This is rho squared. So the whole thing is just c squared sine squared theta delta. So we see what we have calculated here is a determinant of the t phi block of the metric. Here, yeah, the determinant of the negative, the determinant, minus the determinant of the t phi block of the metric. And we have seen that this is proportional to delta. So this determinant becomes 0 if delta becomes 0. Delta equals 0 is the horizon. Yeah? So the metric, this block of the metric, degenerates on the horizon. That's a typical characteristic of the horizon. Oops. Of course, it's not really a true singularity, it's only a coordinate singularity. Yeah, in the Schwarzschild case, look, in the Schwarzschild case, this is just GTT times R squared. R squared never becomes 0, and GTT equals 0 is the horizon in the Schwarzschild case, right? So this expression becomes 0 on the horizon. Okay, now I can insert this into my expressions for t dot and phi dot, and then I have solved, the first half, actually by far the easiest part of the geodesic equation, namely the phi part and the t part. So I have now minus e, what is this? I can't read my own handwriting. It's a g phi t, right? G phi t up there. G phi t is, oh my goodness, g phi t is minus 2mr sine squared theta over rho squared times c. And this comes with an e. I have the e already written here. Then minus L times GTT. Minus L, where's GTT? GTT is c squared. Is it? It's L times GTT. I think it's correct.
But there is an A missing in the first term. It is minus MR and A.
Thank you. That's it. Okay. 2mr over rho squared. Yeah, that was that. And on the other side, I have this determinant with one sign, yeah, with the same sign as I have it here, times phi dot. So I can divide this whole thing by this expression here. So I divide this by delta c squared sine squared theta, and that's my phi dot. Okay? So I have solved for phi dot. Maybe I can simplify this a little bit, write it a little bit nicer. So I have phi dot, oops, is equal to what? It is equal to E 2m RA, the sine squared theta cancels. I have 1c in the denominator, c delta rho squared. And from the second term, well, I think I cannot do much with this. Maybe write it in this way, 2mr, and then I have rho squared delta r, the c squared cancels. That's it. Okay, that's phi dot. So that's our first, first component of the equation of motion in first order form. Now I do the same thing for the t dot. Then I have minus e g phi phi. G phi phi I have to read there. Sine squared theta r squared plus a squared 2mr a squared sine squared theta divided by rho squared. And then minus L gt phi. This gives another minus sign, 2m ra sine squared theta over rho squared times c. Okay, and the whole thing I have to divide by the determinant with the same sign again, with a plus sign. So divided by c squared delta sine squared theta, and that's phi dot, t dot. So I can simplify this again a little bit, not very much, but a little bit. So this is minus e, the sine squared theta goes away. Then I have rho squared r squared plus a squared plus 2mr a squared sine squared theta. I cancelled the sine squared theta, so I have c squared delta rho squared. And here I have plus L 2mRA sine squared theta. Only one c in the denominator, delta. The sine squared theta goes away. So that's it. That's the t dot equation. So if we had solved the equation of motion for the t and the theta component, then we could insert, for the r and the theta component, we could insert r as a function of the curve parameter and theta, which is inside here and here, theta as a function of the curve parameter, and then we would get phi from this equation. And in the same way we would get t from this equation. But this necessary step to solve the equations for rho of the for r of the curve parameter and theta of the curve parameter, this is much more difficult, and we will do this now.
Is there a sign mistake? Because when I have
Probably.
the momentum, then t dot is negative because e is positive, right?
Yeah, it looks that way.
So
Yeah, you're right.
Divide by minus the determinant.
GT phi?
Well, the determinant is gt phi squared minus. So this is what you calculated.
Oh, yes, right. There's this little minus sign in the bracket which I overlooked. Yes. So I have a minus here, and then the signs are just the other way around. Thank you.
For the angular momentum term as well, right?
Sorry, I made it in the wrong place. Here. That's
so
it.
I think t dot is positive.
Yeah, now it's fine. Thank you. Okay, so this was this. So this was the status, until 1968. So, and then Carter came along, and he found this additional constant of motion. How did he do this? He did not work in the Lagrange formalism, he worked in the Hamilton-Jacobi formalism. I hope you remember how, from your mechanics course, how to switch from the Lagrangian formalism, from the Lagrangian to the Hamiltonian, and then to write down the Hamilton-Jacobi equation. And how do you usually try to solve the Hamilton-Jacobi equation? At least the first thing you would try is to make a separation ansatz. Yeah? And that's what Carter did for this problem, and he found it worked. And the separation constant was the additional constant of motion. Yeah? So I will now follow this line of thought here. Yeah?
How is it clear that you can just use this Hamilton?
Well, the passage from Lagrange to Hamilton formalism, where there's a non-degeneracy condition, I will do it in a minute, you will see that this non-degeneracy condition is satisfied. Yeah? You remember the Hessian of the Lagrangian must have a non-vanishing determinant. If this is possible, then you can always switch to the Hamilton formalism. And for the geodesic equation, that's always the case. We will do this in a minute. And if we have the Hamilton formalism, then we can do Hamilton-Jacobi. And of course, doing a separation ansatz is just a try. Yeah? In actually in almost all cases, it does not work. Yeah? It's just a very special class of problems for which it does work. But this is one of them, fortunately.
But can one see it from the beginning?
No, I think one cannot.
So
Well, the Kerr metric was found in 63, and the Carter constant was found in 68. So you can imagine that it's not quite obvious. Yeah? I think it was 68. Maybe I'm wrong by one year or something like that. But it took a couple of years. And actually, the Kerr metric was studied very, very intensively immediately after it came out. Yeah? There were special conferences devoted just to the Kerr metric, where Penrose organized such a conference, where he gave most of the talks himself and studied the Kerr metric in all details. And so people were very, very much excited when this metric came around, because they immediately realized that this is the most important solution of the Einstein field equation since Schwarzschild, since 50 years ago, almost 50 years ago. So it was studied very intensively, and that under this condition it took so long to find this constant of motion is a strong indication that it cannot be quite obvious. Yeah? Another question? Yeah, what is missing?
The last term.
Yeah.
Rho squared missing.
Let me see. The rho squared. Yes, the rho squared should be still there. Thank you. Okay, hope now it's correct. So now the goal is now to find a fourth constant of motion. And this is, I emphasize, it's very special to the Kerr metric. If you have any axisymmetric and stationary spacetime, another axisymmetric and stationary spacetime, the spacetime around some rotating star, yeah? In general, there will be no such force constants of motion. It's very special for the Kerr metric. Okay, so we do the passage to the Hamilton formalism. Yeah?
Was it clear from the beginning that this concept exists?
No, it was not. That's what I'm saying. It was absolutely not clear.
But how can then you assert that there is no such concept for a star or something like that?
I'm sorry, I didn't understand.
How then can you assert that there are no such concepts for objects with multiple...
Ah, okay. What I mean is they have not been found until now for... but no, it's from generic... considerations of genericity, it's clear that it's only a subset of measure zero which can have an additional constants of motion. Yeah? So in the generic case, spacetimes which are just axisymmetric and stationary, no additional symmetry, such spacetimes in the generic case have no additional constants of motion. So maybe I should say, before I do the calculation, I should make a more general remark about constants of motion. If you have taken a good course in mechanics, then you know that there's always a relation between symmetries and constants of motion, which is known as Noether's theorem. But Noether's theorem refers to symmetries upstairs, on the tangent bundle or on the cotangent bundle, on the phase space, yeah? Not on the base manifold. Yeah, every constant of motion is associated with a symmetry on the phase space, but not with a symmetry on the base manifold. And in the geodesic case, the ones which are associated with symmetries on the base manifolds, these are the ones which are associated with Killing vector fields, which are really symmetries of the metric on the base manifold. The constants of motion are then linear in the momenta. Yeah? So the ones which are linear in the momenta, they are associated with symmetries on the base manifold, and they are easily found, because it's not so difficult to find out what kind of symmetry your metric has. And then there are additional constants of motion which are not linear in the momenta, which are quadratic or higher order, or maybe not polynomial at all. And they are difficult to find. And the Carter constant of this type is actually associated with a constant of motion which is quadratic in the momenta. That's what one calls the Killing tensor of second rank. But I will not introduce this notion here. So there is a symmetry. It has something to do with the symmetry, but it's a symmetry which is not easily discovered. It's a symmetry on the phase space, not on the base manifold. Okay, let's do the passage to the Hamiltonian formalism. Hope you remember this. If you have a Lagrangian L, then you introduce canonical momenta, which are just dl by dx mu dot. And in our case, where the Lagrangian is just 1/2 G, I need another index, let's say tau sigma, x tau dot, x sigma dot, then this derivative is easily calculated, and you get it is G mu sigma, x sigma dot. And the passage to the Hamiltonian formalism is possible whenever this equation can be solved for the velocities. And here this is obviously the case because the metric is invertible. Yeah? So this implies that we can easily solve this for the x dot, say x dot sigma. Then we have, it's just the inverse metric, the metric with the contravariant components times p mu. And then we can insert this into the Hamiltonian. The Hamiltonian, that's now a function of x and p. So this means the 4x coordinates, this means the 4p coordinates. So in our case, this is t, r, theta, and phi. And this is pt, pr, p theta, p phi. And how is it defined? Quite generally, if you recall the definition from your mechanics course, it is p mu x mu dot minus the Lagrangian, which basically depends on x and x dot, but we want to have a function of x and p, which means that we have to express the x dots everywhere in terms of the p's here. But that's easy in this case. So it's written in the line above. So this is p mu. Now I have to rename the indices again. I need x, or let me write it p sigma. Then it's easier to read it off. So I have p sigma now, x dot sigma, and that's what is written here. G sigma mu p mu. And the Lagrangian is, well, this equation simply means x dot is just the p with the index raised. Yeah? So if I replace the Lagrangian, this expression here, this is just the p with the index raised. So I can switch it again, and then I have just minus 1/2 g sigma tau p sigma p tau. And you see 1 minus 1/2 gives plus 1/2. So we have our Hamiltonian. And this was for a completely arbitrary metric. Yeah, this holds on every space-time. The Hamiltonian is 1/2 g mu nu p nu. And so it's the same as a Lagrangian. Yeah, it's the same as a Lagrangian, just expressed in terms of different variable. Not in terms of x and x dot, but rather in terms of x and p. But it takes the same values. So in particular, because L was a constant of motion, which was associated with this constant which I called epsilon, h is associated with the same thing. So h is also a constant of motion. Of course it is a constant of motion. That's always the case if the Lagrangian or the Hamiltonian does not explicitly depend on the curve parameter, which is the case here. Yeah? So it's obviously a conserved Hamiltonian. So it is the same, takes the same value as a Lagrangian, so it's minus 1/2 epsilon. Okay, and now I want to do the Hamilton-Jacobi thing. So the Hamilton-Jacobi equation. So how does this work? One method of solving the dynamical problem associated with the Hamiltonian is that you write the equation. The Hamiltonian is this constant of motion, and you substitute for the p the derivative of a function s. That's the function which you want to find. Then this becomes a partial differential equation. And if you are able to solve this partial differential equation in the sense that you find what is called, how is it called? A complete integral, I think is a word. Yeah, the complete integral. This is an integral which depends on so many constants of motion that you can fit your momentum to any possible initial condition. So that you have, for any possible initial condition for the p, you have a solution where your function s, the gradient of your function s, points us just in this direction at any point. And that's what we try to do now for this problem. So the Hamilton-Jacobi equation quite generally reads, let me write it in symbolic way like that. This means that I write wherever I have a momentum p mu, I write the partial derivative d by dx mu of a function s. And this is, in our case, it is minus 1/2 epsilon. Otherwise, we have the value of the constants of motion h, which you want to study. And in our case, this means, well, what is the h? The h is written here. This just means g mu nu, which is a function of x. And then these expressions, d mu s, d nu s is equal minus 1/2 epsilon. So the 1/2 can be cancelled. So that's a partial differential equation, right? It's a partial differential equation for a function which lives on the base manifold. It depends on the coordinates, t, r, theta, and phi. And if we find a solution which involves as many constants of motion as our system has degrees of freedom, that's four independent. The epsilon is one of them. Here the epsilon counts. So I need three additional ones, and I'm done. And what one does is, in order to find such a solution, the first try, which one always does, is that one makes a separation ansatz. So one tries to find a function s, which is dependent on t, phi, r, and theta, as a sum of terms, where each term depends only on one of the coordinates. So one tries to find this as in the form st, which depends only on t, plus s phi, which depends only on phi, plus sr, which depends only on r, plus s theta, which depends only on theta. And now you know from your mechanics course that you can always separate off a coordinate which is cyclic. Yeah, and that's the case here. T and phi are cyclic. Yeah, so your Lagrange function and the Hamiltonian function do not depend on t or on phi. So you have this associated with a constant of motion, which is just the corresponding momentum. Yeah, so pt and p phi are constants of motion. And whenever this is the case, then it's clear how what kind of ansatz you do for these functions. This is just linear in t, where the coefficient is the corresponding constant of motion. So in our case, this is minus e. And for this correspondingly, phi L. So this always works for these two terms. What is not clear at the moment is whether the rest can really be written as a sum of a function of r only and of theta only. But let's try if it works. Let's try if it works. So that's the ansatz which we have to plug into the Hamilton-Jacobi equation. We have already, excuse me, what I, yes. I said I need 4 constants of motion, right? I have the epsilon here, I have the E and the L, I need one more. And then the additional one comes into the game, as we will see in a minute, as a separation constant when this ansatz works. If it does not work, then we cannot find a 4th constant of motion in this way. But in this case, it will work. So we plug this ansatz now into the Hamilton-Jacobi equation, and then we have to calculate for a while. Hamilton-Jacobi equation. Ah, yes. Now we encounter a problem. Well, not a problem, but we have some work to do. For the Hamilton-Jacobi equation, I need the G mu nu with the upper indices. They are not on the board yet. We have to calculate them. Yeah, we have to calculate them. So this will be a little bit tedious, but let's just introduce this ansatz. So let's begin with the TT component. So I have GTT, and then here's a T derivative. The T derivative gives minus E, but it is squared, so it's just E squared. Then I have GT phi, 2 times GT phi. Derivative with respect to T, derivative with respect to phi. One is minus E, the other is L, so I get minus E L. And then I have a G phi phi term, L squared. And then the other ones, they are easy. So here I have plus GRR. And the derivative with respect to R, I just denote it by a prime. Yeah, I take the derivative with respect to the argument. That's what the prime means. Plus G theta theta, that's theta prime of theta 0. So that's the equation we have to solve. We have to see if this equation admits a solution, a pair of solutions as R of R as theta of theta. And as you see, we need these coefficients. Oops. So we need to calculate. Well, actually, that's not too bad because we have only one off-diagonal element. Yeah? It would be very easy if the metric would be diagonal, then it would be quite easy. If it has many diagonal elements, then it's quite tedious. Need to calculate the G mu nu. So I have a matrix of the G mu nu with lower indices. Let me write it in this way. Yeah, this means a matrix which is formed out of these things. So this is, what do we have? We have a GTT, we have a G phi phi, we have a GRR, and a G theta theta, and the only off-diagonal element is here, GT phi, GT phi. It's symmetric, so GT phi is the same as G phi t, and all the rest is 0. Okay, let me see if I can manage to invert this metric. This matrix. So you see it has a block form. Yeah? So the inverse of this matrix has just the inverse of this thing in this block and the inverse of this thing in this block, and the rest is 0. So it's not too difficult actually. So the inverse matrix is the following. The inverse of this here is G phi phi divided by the determinant GTT G phi phi minus GT phi squared. Then this is a 1-2 element, so it comes with a minus sign. GT phi is a minor. GTT G phi phi minus GT phi squared. And here I have the same term as here, minus GT phi GTT GT phi G phi phi minus GT phi squared. And here I have GTT divided by this denominator, which is just the determinant, which fortunately we have calculated already. So I don't have to do it again. So that's this block. Oops, I need more space. Well, that's a much bigger bracket here. So, well, this is easy. To invert this is no problem whatsoever. This is 1 over GRR, 1 over G theta theta. 0, 0. Yes. 0, 0, 0, 0, 0, 0. So if you multiply the two matrices out, then I hope you will get the unit matrix. GTT, G55, G5, yes. This comes with a minus. Yes, I think everything is fine. And, well, these things we have calculated already. So we can now write our metric, our inverse metric. So G mu nu, P mu, P nu. That's the expression which we need for the Hamilton-Jacobi equation. This is G, or G55 is correct. G55 PT squared minus 2 GT phi PT P phi plus GTT P phi squared divided by this determinant. And the other two are simple. So this is PR squared divided by GRR plus P theta squared divided by G theta theta. Okay? And yeah, I can read this. G phi phi was sine squared theta R squared plus A squared plus 2mr A squared sine squared theta over rho squared. Oops, PT squared. Oops. Then minus 2 times the mixed term. This is plus 4m. RA sine squared theta over rho squared. And plus GTT is minus C squared 1 minus 2mr over rho squared, PT squared, P phi squared, sorry. And the whole thing is to be divided by this determinant, which fortunately we have calculated. Where is it? Should be somewhere on the board. Here. And this continues here. It's this. Which sign? I have GT phi squared minus blah, blah, blah. That's just the negative of this here. So I have minus C squared sine squared theta delta. And then the two easy terms. PR squared, where's GRR? GRR is up there. I have to take the inverse, delta over rho squared. And P theta squared, the inverse is 1 over rho squared. Okay, that's it. So I can now insert this into our Hamilton-Jacobi equation. So what do I have to do? I have to replace the momenta by the derivatives with respect to r, and then I have to equate this. What did I write there? Why is there a 0? There's no 0. I wrote a 0 here. Nobody protested. This is true for light, but it's not true for time-like geodesics. Yeah? The whole thing, what's the equation? The equation is h is equal to minus 1/2 epsilon. I have divided out the 1/2, so this should be minus epsilon, right? Minus epsilon. Okay, and that's the equation I have now to evaluate. Let me see, can I put this here? Yes, I think this should work. So I write the right-hand side of this equation. So the first bracket, the sine squared theta cancels. So I have r squared plus a squared plus 2mr a squared sine squared theta divided by rho squared. Sine squared theta is gone. Pt squared is e squared. I have a minus sign, and I have c squared delta. That's the first term. Then the second term, this is plus 4mRA sine squared theta divided by, I have 2 times a minus sign. pt is minus e and the minus is there, so I have a plus e, L here. And in the denominator I have rho squared, c squared, sine squared theta delta. The sine squared theta cancels. So, okay, let me write it this way to save a little bit space. That's the second term. And the third one, this is minus c squared cancels against c squared, 1 minus 2mr over rho squared, pt squared is L squared. I have 2 times a minus sign, so it's plus, c squared is gone, sine squared theta delta. And the remaining terms, plus delta over rho squared sr prime of r squared, plus 1 over rho squared s theta prime of theta squared. And the whole thing is minus epsilon. Okay, so what we have to try now is, we have to try to separate the r from the theta. Yeah? To rearrange terms in such a way that on one side of the equation we have only a function of r, and on the other side we have only a function of theta. If that's possible, then we are done. If it's not possible, the whole ansatz doesn't work, then we would have to think about something else. But fortunately it does work. So, well, first thing, well, everything has a rho squared in the denominator, so I think it's a good idea to multiply everything with rho squared. And then let's see what we can work out on the right-hand side. Then I have minus e squared divided by c squared delta, bracket, r squared plus a squared. Well, I want to separate the theta and the r terms, so I think I need to write out the rho squared. So rho squared was r squared plus a squared cosine squared theta. And then I have the second term, plus 2mr a squared sine squared theta. Oops, the e squared is already there. Okay, second term I have multiplied with rho squared, so this is just 4mr e L divided by c squared delta. That's fine, it depends only on r. Remember, delta involves only the r, not the theta. This term, it involves both again. Then I have plus, I have multiplied with rho squared. So I have here the rho squared, which is r squared plus a squared cosine squared theta, minus 2mr, no bracket, minus 2mr. C squared, no, that's an L squared, sorry, my handwriting is so awful. L squared, sine squared theta delta. And then the other terms are obvious, plus delta SR prime of R squared, plus S theta prime of theta squared. So let me see. Where do I have to do some work? The rho squared on the left-hand side. I should also write this out. R squared plus A squared cosine squared theta. Let's try to separate the R terms and the theta terms on the right. So the free factor depends only on R. When I multiply this with an R squared, then I have only terms which involve R. So this is R squared plus A squared. The other terms, the other terms are, let me see, minus E squared C squared delta. Now this I have already finished with. So here I have R squared plus A squared. Let me invent a term which is not written there. Minus 2mr times A squared cosine squared theta. Of course, I have to add this term again. Plus 2mr a squared cosine squared theta plus a squared sine squared theta. That's just a squared. Okay? You see, that's the same thing. So this term and this term together gives this here. Yeah? It's 2mr a squared minus 2mr a squared cosine squared theta. That's 2mr a squared sine squared theta. I copy the next one. Anything wrong again?
What's the minus in front of e squared?
The minus in front of e squared. For the first term, right, thank you, yes. Plus 4m ra el divided by c squared delta. Nothing to do with this. What can I do here? Yeah, I do a similar thing here. I write r squared plus a squared minus 2mr. And then, because I have only a squared cosine squared theta, I have to subtract minus a squared sine squared theta. That's the same as this bracket. A squared divided by sine squared theta delta. Okay, the rest I just copy. Plus s theta prime squared. So I think now I'm on the right way. So this depends only on r, fine. The second term depends only on theta, fine. And on the other side I have this depends only on r, again fine. Let's see, what can I do here? This is delta. This delta cancels against this delta, so then I get minus e squared a squared cosine squared theta divided by c squared. Fine, depends only on theta. And the last term, minus e squared 2mr a squared divided by c squared delta, depends only on r, also fine. Plus 4mr a el divided by c squared delta. Let's see, what can I do here. This is delta, cancels against this, and I have just L squared over sine squared theta. And the rest is minus a squared L squared over delta. And the other terms are what they are. Okay, and we are now already on the right track. Now comes the problem. What can I erase? Maybe not the equation for phi dot. Hope I don't need the equations of motion and as a metric coefficients anymore. Let me see. I hope so. I have to erase something. So. Let's do this here. Okay, hope it will dry soon. We can continue. Where are we? Oops, here we are. Okay, what else can I do? What else should I do? You see, on the right-hand side we have E squared terms, L squared terms, and E times L terms. Maybe it's a good idea to combine them into squares. So, which ones? Let me see. First I should. What's going on here? This is a funny term. I think that's not correct. Let me check. I think this doesn't look good. Wait a minute. Epsilon is something like c squared. There's something with the dimensions wrong, right? I'm afraid. Okay, I do the separation and then we check again. I'm afraid there's something wrong, as usual. Squared. No, I think these two terms, they look not good. They don't look good. That's squared. Wait a minute. Maybe here I have a sine, here I have a cosine. Maybe if I transfer this into a sine term, if I write this as 1 minus sine squared, this could be the solution. Yes, I think this could work. So let me write it again. Minus epsilon r squared minus epsilon a squared cosine squared theta is equal to minus, the first term is fine, r squared plus a squared, what's in the denominator? C squared delta. Okay, and the next one I write in the following way. I write minus e a squared over c squared. And then plus e a squared sine squared theta over c. That's the second term there.
In both cases, e squared.
Right, thank you. Yeah, should be this way. Okay, let's see. Minus e squared. Do I have to write this whole rubbish again? I think I have. Ra squared divided by c squared delta. Yeah, everything else is fine. Plus 4m Ra EL c squared delta plus L squared over sine squared theta minus a squared L squared over c squared. No, that's a delta, sorry. Yeah. Plus delta s r prime squared plus s theta prime squared. So now let me see. Now I can combine this term, and this term. These three terms on the right-hand side. Oops. Left-hand side as what it was. So I write everything above c squared delta. And then I have e squared r squared plus a squared. Here I have multiplied numerator and denominator with delta. So I have minus a squared r squared plus a squared minus 2mr. The square bracket is delta. And here I have minus, are the signs correct? No, the first thing has a minus, right? First thing has a minus 2mr a squared. And this bracket is closed.
But I guess both minus in the bracket must be plus 2.
Where the brackets are, wait a minute.
Brackets.
Yeah. I think that's right now? Okay, good. Yeah. That's 2mr. Yes, and these two terms cancel, right? Yes, I think that's it. I think we are on the right track. So where do I have something without the angle? This is also without the angle, only r dependent. And and these terms. Oops. Okay, and now I'm completing a square. So I write this in the way that, what do I have here? Here I have minus e squared over c squared delta. And inside the bracket, I have r squared plus a squared squared. No, oops. R squared plus a squared squared. And I write this by completing a square. So let me see. So that's this term here now. I combine this with.
Isn't one term missing this singular?
Which one? Ah, this one here, right?
Yeah.
This one. Thank you. A squared sine squared theta c squared. Yes, that's very good. That's very good. I will combine these two. Then I think I combine this here with this. So, okay, let me write it. Let me write it again. Oops. So this was this, and I combine it with this term here. So this is minus a squared L squared C squared. And I combine this term, no, with nothing. I leave it. RA. So the plan is I want to have squares on the right-hand side. Yeah? So I will complete the square here in order to write this as a square of something, and then the rest should also be a square. But let's see if this comes out as I hope it will. And here I have these two terms. Plus e squared a squared sine squared theta c squared plus delta sr prime r squared plus s theta prime theta squared. So what do I need for completing a square? I add here plus 2el r squared plus a squared ac divided by c squared delta. Now this is a square. This term together with this is a square. Of course I made a mistake, so I have to subtract it again. So I subtract it again. Minus 2EL R squared plus A squared AC over C squared delta. The square cancels. I do the same thing with these two terms, but I should not forget this here. Let me write this here first. No, it is already there. It's already there. So I do the same thing with this here. So I add a square, let's say minus 2LE A squared, no, A sine theta without squares, sine theta C, which cancel. And I add it again, 2LE A C. You see what I've done? I've added two terms, 2 times a 0. This plus this is a 0, and this plus this is a 0. The reason is that I can merge this term with this here into a square. No, this with this here into a square, and this with this into a square. And that's what I do now. Oops. So I have now minus epsilon r squared, and then I hope you are done, is what? So this term together with the first term in the last row should be a square. It is what? It is minus E r squared plus a squared. Both terms have c squared over delta. So this is in the denominator of everything. And this is minus ALC squared. Okay? So these are these terms and this term. Minus, oh, what about the sign? No, this term and this term, sorry. This term and this term, not this here. With a plus sign, right? The mixed term has a plus sign. So 2EL R squared A squared A C, yes, I think that's fine. Okay, then I combine these two terms here, this and this, with this here. This is L over sine theta minus EA sine theta. I can't read my handwriting. Was this a minus? No, wait a minute.
No, just mark the term.
Okay. I shouldn't do this. This is complete confusion. So this was a square. Okay, these are the two squares which I wanted to have, and now I hope that the rest will cancel. So what are the other terms? The other terms are this here. Oh yeah, I think I could continue here. Plus 4mRA EL divided by c squared delta. Then I have done with this, This is still missing, minus 2EL. R squared plus A squared, what was it? A divided by C delta. Then this we have done with, so we have plus 2LEA over C. EL A over C, and the two terms with S of R and S of theta derivative plus S of theta derivative squared. So, and now my big hope is that these three terms cancel. Let me see. C squared delta, then I should write also here a delta. Then it's easier to compare. Here I have what? They all bring a 2ELA. 2ELA. And then we have R squared plus A squared with a minus sign. 2MR with a plus sign. Plus delta. So these three terms cancel indeed. Yeah? We have minus R squared, minus A squared, plus 2MRA. That's exactly delta. So these three terms cancel. My goodness, we really did it. So now we can collect all terms with the r on the one side and all terms with the theta on the other side. So we have minus epsilon r squared. This comes to the other side, plus e r squared plus a squared minus ALC squared over c squared delta. Where else is an r? Here. This goes to the other side, so it becomes minus delta SR prime R squared. And now all the other terms on the right-hand side. Let's begin with this here. This comes to the right-hand side. It's epsilon R squared, A squared cosine squared theta. Then this term is on the right-hand side with a plus sign. Minus EA sine theta over C squared, and this here is on the right hand side with a plus sign. And now you see, this term is independent of theta. No theta anywhere. This term is independent of r. No r anywhere. But the two things are equal. So they can depend neither on r nor on theta. Yeah? And that's what one calls plus k or minus k. Let me check. It's plus k. And that's the famous Carter constant. So it comes about as a separation constant in the Hamilton-Jacobi business. And it allows us to write the remaining two equations, the remaining two components of the equation of motion in separated form. Yeah, we have an equation for t dot, we have an equation for phi dot. With this separation, we now get two separate equations for r dot and for theta dot. And how does this work? Well, we have to solve for SR prime and for theta prime, because these are just the momenta. These are the momenta, PR and P theta. And PR and P theta are related to R dot and theta dot just by the metric, yeah? Raising the indices with the metric. Okay, so let's solve for S. Let's begin with the theta. Let's begin with, or let's, yeah, it doesn't matter. So what is this? If I solve for this expression, then I have on the other side plus k minus this term, minus L over sine, no square, sine theta, not sine squared, EA sine theta over C. And this comes to the other side, so it is minus epsilon A squared cosine squared theta. And if I solve for the SR prime, this comes to the other side. If I want to have it with a plus sign, then I have to multiply everything on the left-hand side with minus 1 over delta. With minus 1 over delta. So I have minus 1 over delta k. And this with 1 over delta. Oops, that looks, I check in a minute. Is this really true? Do I have this in the denominator? Okay, I write it down and then I check. So this would be 1 over c squared delta squared. It can be, wait a minute, this is just the S prime, so that's a P. It's not just the R dot. We have to express this in terms of R dot and then we get another factor. Could be correct. ALC squared, and this is on this side, so it is minus epsilon delta R squared. So this is S prime and S theta prime and S R prime. So that's a derivative of our Hamilton-Jacobi function with respect to the theta and with respect to the R coordinate. This is what is to be identified with the momentum in the corresponding direction. Yeah? So this is nothing but our P theta squared, and this is nothing but our PR squared. But what is this? The momentum was just G theta mu x mu dot, and the whole thing is squared. And because the only component with the theta is the G theta theta, this is just G theta 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 dot. And this is, what is g theta theta? This was rho squared, right? So this is rho to the fourth theta dot squared. And what is PR? PR is gr mu x mu dot squared. There's also only one component which has an r, that's the grr component. Grr r dot squared. And grr was rho squared over delta, if I'm not mistaken. No, I erased it, but I hope it's correct. It's rho squared over delta. So it's rho to the fourth over delta. That's fine, that kills the delta. Good. R dot squared. And these are the desired equations for r dot and theta dot. It's quite interesting, they come with a square. So if we solve this, we have to be careful that we have a plus sign and a minus sign, right?
Awesome.
Yeah?
Shouldn't this delta be in the denominator? And
In the
so
last
in
term.
the last epsilon term on the left.
Here.
Yes.
Is that true? Let me see. Yes, you're right. Thank you. That's it. Well, that makes the equation a little bit simpler. Good. Theta square. Oh, let me write the rho to the 4 on this side. We can leave it here. But let me. It's this equation. I just copied it. Minus L sine theta minus EA sine theta divided by this thing squared minus epsilon A squared cosine squared theta. And the other one I multiply with delta, rho to the fourth r dot squared is a something is wrong with the delta. It shouldn't go away everywhere.
Divide by multiply with 1 then, not.
Did I make a mistake somewhere with the delta? Let me write what I get, but I think it's not the correct thing. I have a minus k here. I have minus e r squared plus a squared minus a lc squared divided by c squared. I multiplied with delta, so there would be one delta left. And here I have no delta whatsoever. I think that's not right. That's not right. I think I need a delta here in the denominator and also here, in the numerator and also here. Let me check. So there is a mistake somewhere, as it was to be expected.
We guess that this must be delta squared.
Yeah.
In
GRR is rho squared over delta.
Thank you. Very good. Very good. Yeah. GRR is rho squared over delta. And the whole thing is squared again. So I have rho to the fourth over delta squared. And then I get indeed a factor delta here. And I think then it's correct. Get a delta here, delta here, delta here, and that's it. So these are the remaining two equations. And now we are done. We have reduced our equation of motion to first order. Yeah? So we have still on the board the equations for t dot and phi dot, and these are the equations for theta dot and r dot. So how do you solve the geodesic equation now? Well, you have for each choice of the constants of motion, you get one geodesic. So you have 4 constants of motion: epsilon, L, E, and K. These are the 4 constants of motion. They correspond to initial conditions for the initial vector. Yeah? And with this, you solve these equations. This involves only r on the right-hand side. There's one subtlety. This depends also on theta. We have to talk a little bit about this, how to make this into an equation which really involves only r. This will be done by a reparametrization of the curve. But apart from this, I have only r on the right-hand side, so I can solve this for r as a function of the curve parameter. Solve this for theta as a function of the curve parameter. Insert it into these 2 equations and get t and phi. Okay, and that's how it works, and we will discuss this for light-like and time-like geodesics in some detail. Sorry, I'm already over time. So have a nice weekend, and on Tuesday we will continue with the geodesics in the curve space set. So we will harvest what we have sowed today. So then we'll talk a little bit about physics again after doing a lot of calculations. Okay, see you then.